Continuing in the third quarter, we get to gases. Gases are covered in Chapter 12, and all the gas law relationships use kinetic theory as their foundation. That is, we assume three things. Gases are made up of particles, the particles are in constant random motion, and the particles move independent of one another in straight lines until they have a perfectly elastic collision. That is, they don't lose any energy. So it's important to know some of the basic definitions and units that apply to gases. We commonly use three different units to measure gas pressure: atmospheres, kilopascals, and millimeters of mercury. Also, STP, or standard temperature and pressure, is a term that's been used as far back as mole conversions in stoichiometry. But since gases behave differently depending on their atmospheric conditions, it's important to note that we consider standard temperature as 0 Celsius or 273 Kelvin as you convert. So there's three basic gas laws that we need to know. Number 70 uses what we call Boyle's law, which describes pressure and volume as inversely proportional. In other words, if the volume of the gas goes down, the pressure goes up, and vice versa. So looking at this problem, we have a gas that starts out at a pressure of 500 millimeters of mercury and a volume of 5 liters, but the volume changes to 2.5 liters. The volume is going down, so the pressure is going to have to go up. The equation for Boyle's law is given here. P1 times V1 equals P2 times V2. So when we substitute the values into the proper places, what we find out is that the pressure does indeed go up, and it goes up to 1,000 millimeters of mercury. Number 71 uses Gay-Lussac's law, which describes pressure and temperature as directly proportional. In other words, if the temperature goes up, the pressure goes up as well, and vice versa. So in this problem, we start with an initial temperature of 20 degrees Celsius and a pressure of 100 kilopascals, and they want the pressure to be increased to 200 kilopascals. So the question is, what temperature do we need to get the balloon to increase to in order for that pressure increase to happen? One thing to note here is that as you use Gay-Lussac's law, P1 over T1 is equal to P2 over T2. The temperatures for all the gas law calculations always have to be in Kelvin. So we have to convert that 20 Celsius by adding 273 to get it to be 293 Kelvin. So we've got 100 kilopascals that it started with at a temperature of 293 Kelvin is equal to the new pressure, 200 kilopascals, and then we're solving for T2. In this case, 586 Kelvin, or if you want to put it back to Celsius, subtract 273, and you get 313. There's also another gas law, which is Charles' law. There's not a problem here involving Charles' law, but Charles' law says that the volume and temperature of a gas are also directly proportional. And again, temperature would have to be in Kelvin if you were to do any calculations for that. And then finally, I want to look at number 77 here. Number 77 is asking about which state of matter has the greatest kinetic energy. Basically, a way to think about this is that solid particles are very organized, they're attracted to one another, they're not moving very quickly, and as you heat them and the solid begins to melt, you form a liquid. The liquid particles start to move and flow a little bit more, and they have a bit more energy because they're moving a bit more. But then as you continue to heat it and gases are formed from the liquid, the gases have the greatest kinetic energy because their movement is the greatest. Kinetic energy has to do with energy of movement of an object.